we started off this whole different section yesterday that we didn't do on before. And before we've looked at derivatives, but now we're just kind of looking at graphs and figuring out what the highest value is, what the lowest value is. It's really not, you might not see the application to calculus yet, but we did introduce something a little bit new. Is anyone walking in? Does anyone need a set of guided notes from Monday or from yesterday? Do you need the set of guided notes from yesterday? Good. All right. So we talked about how to find the absolute maximum and minimum. And remember, the absolute extrema or max and min are the highest value that the function reaches and the lowest value that the function reaches. Okay. You're essentially like looking up the range of the function, right? Okay. Now, on the other hand, we talked about local maximums and local minimums. And these were like our peaks and valleys of the function, right? So if it turns around at a specific point, it's a local max. And if it turns around and looks like a valley at another point, it's a min. We did some funky examples that I told you I would probably ask you on WebAssign, but I probably wouldn't ask anything too crazy like this on a test or quiz, but it did give us a little bit more of an idea of what a local max and a local min actually is. But I'm not going to spend too much time looking at that. Then I gave you a random challenge. Okay, so what we did is I asked all of you to draw a function in a very specific way. Okay, so I asked you to draw a function, and I remember a function is something that passes the vertical line test, right? So you can put a vertical line through it and not touch the function twice, okay? I also asked you to make the function continuous, which just means you can draw it without picking up your pencil, right? So no jumps or holes or anything like that. And I also told you to draw this function on a closed interval. And what that meant was the endpoints have to be filled in, right? So make sure that there's closed endpoints. Now, I walked around the room and I told you guys to be a little bit creative. So I found some funky equations as I've been walking around here. And actually, I think I'm going to start with the bottom one here and work my way up. Okay. So after I told you to draw your function, I asked you to find the absolute max and absolute min of each. And let's just do that. So on this function here, the one that's a straight line, what's the absolute maximum? 4, good. And remember, when we talk about the maximums and minimums, we're always writing a y value. So we're not going to write 3, okay? Now, there only can be one absolute max, or at most one. What's the absolute min? -3, good. Okay, so that's kind of a basic function, but really nice job writing that one out. The next one that we did, moving our way backwards, this one is a little bit different because it's got like a jagged edge to it. I actually think the person who wrote this up didn't actually mean to make this a jagged edge, but it ended up looking like one, which is fine. I like the jagged edge. And that's totally fine. It's still continuous. What's the absolute max of this one? 4. And what's the absolute min? -4, good. All right. Then we did this one, which actually was supposed to have a jagged edge in it. I like this graph too, because it started at the same point. So the beginning is at the same height as the end. What's the absolute max here? 4. What's the absolute min? 0, good. All right, I think we're getting a little good at this. Jude wrote this one, which I thought looked really hilarious. What's the absolute max of this one? 4. Absolute min? -4. Okay, I promise I'm going overkill on this, but you'll see my point. Okay, this second one, what's the absolute max? 2. Absolute min? -3. Okay, and finally, John wrote this one up, which I thought was cool. It was just a straight line. What's the absolute max here? 0. What's the absolute min? 0. Good. Okay, so we had all these crazy functions. We found the absolute max and absolute min. Remember, we can have a function that does not have an absolute max or an absolute min. We've looked at examples like that before. Do you think that you could draw a function like the way that we've drawn it before and not have an absolute max or an absolute min? No, right? So no matter how you draw a continuous function on a closed interval, there's always going to be a absolute max and an absolute min, okay? Now, there's a theorem that says this. We call this the extreme value theorem, okay? Extreme value means absolute maxes and absolute mins, okay? And it's exactly what we just did, okay? So I know this looks like a bunch of words being thrown on this page here, but let's just say we have f, and it's a continuous function on a closed interval. So continuous doesn't have any gaps or holes in it. And it's on a closed interval, which means the endpoints are solid, okay? And let's say that this is true, okay? Then it says that f has to attain an absolute maximum and an absolute minimum for some two numbers on A and B. Okay, so that's all this theorem says, okay? Now, I will not prove this in class. This is a very hard theorem to prove, so I'm not going to do that for you. If you would like to, you can ask your discrete math teacher to do it and make them mad, but don't make me do it. But let's just go through some examples and see some things that we should think about, some things that make the extreme value theorem true or not true. Okay, so in example 9, I have this function here. Okay, now what's the absolute max of this function? Doesn't exist, right? There's an open circle at the highest peak of this. So there's actually no absolute max. Wait a minute, I thought the extreme value theorem said that there has to be an absolute max. What's going on here? Good, right? The extreme value theorem only applies to things that are continuous. Is this continuous? No, right? This is not continuous. And I'm not going to make you prove it or anything using what we did before, but it's very obviously not continuous because I try to draw it, I would have to pick up my pencil and then try to continue drawing, okay? Because this is not continuous, the extreme value theorem doesn't work for it, okay? So we can't say that the extreme value theorem applies because it doesn't satisfy the two things that it requires, okay? So the extreme value theorem doesn't apply. Okay, so that's why it doesn't seem like it works here because it's not supposed to work. Let's take a look at example 10. What's the absolute max of this one?
Doesn't exist.
Doesn't exist. Okay. Well, thought the extreme value theorem worked here. What's going on here?
It's not on a closed circuit.
Yeah, not on a closed interval, right? Remember, it says that we have to have closed endpoints, which isn't true here. And it's not true here, right? There's no solid endpoint at both ends, okay? So this doesn't apply. Does not apply. And that's because we need a closed interval, okay? So need a closed interval. Okay, yeah.
This is also the same thing as the intermediate value theorem.
The intermediate value theorem, what did that one say? Why am I blanking on this? I don't think it's the same. What did the intermediate, man? We learned about the intermediate value theorem, right? It's been a while. I know how to spell, I just spelled it wrong. I think we did go over the, why am I blanking on this? I think it's Thursday and I'm just like, ugh. Oh, okay. Okay, yeah, we did go over the intermediate value theorem. Let me tell you the difference. Okay, that's a good question. I don't know why my mind just blanked here. Okay. Okay, don't confuse the extreme value theorem with the intermediate value theorem. Okay, let me show you what the intermediate value theorem says. Okay, I think we said intermediate value theorem is if we have a function that is continuous, right? And that was like the only thing that we needed, something that was continuous, like a polynomial, right? And we also had, so our function kind of looks like this, right? And it might do this. And let's just say we have f of a and f of b, right? Okay, what the intermediate value theorem says is if I take any number between f of a and f of b, so that's f of a, and this is f of b. So for example, I don't know, this number here, I know that the function is going to have a value at that point. Does that make sense? So that's what the intermediate value theorem said. It doesn't say anything about a closed interval, and it's not telling us about maxes and mins. It's telling us about like hitting a certain number. Okay, but that's a really good question. Yeah, so intermediate value theorem is a little bit different, and we're not really considering like maxes and
So it's
mins
just
there.
like confirming that there's a value there if it's in between those 2 points that's continuous.
It's very useful when you're like, you have a function and you want to see if it has a solution. So I think the question I asked you on the test with the intermediate value theorem was, we have this function and I know like f of a is here and f of b is here, okay? And I want to know, like, does it have a solution, which means does it pass through the x-axis? If it's continuous, then it will.
Right.
Yeah. So that's a really good question. There's a lot of theorems going on here, so I wouldn't. So don't confuse the intermediate value theorem with the extreme value theorem. They're a little bit different. Any other questions? All right. The next theorem we're going to talk about is something that I don't want you to actually know. Okay. So I have a point which is where I'm going with this, but I don't expect you to like know this. Okay. So don't like memorize it or don't spend too hard knowing it. Okay. Okay. And this theorem is called Fermat's theorem. Okay. Let's say we have a function and it has a local max or min. Okay, so it has a max here, it has a min here, okay? And also at these local maxes or mins, the derivative actually exists, okay? If this is true, then the derivative is equal to 0. Now we've talked about this before. We know that if there's a turning point, the derivative is equal to 0. Let me just show you some reasons why we don't actually care about this theorem, okay? Let's talk about this one. We have f of x equals x cubed. It looks like the disco man, right? And at x equals 0, what do you think the derivative is?
Doesn't exist.
Oh, you're talking about, this is a horizontal kind of function. Vertical asymptotes are where it doesn't exist. Yeah, but this derivative is actually 0 because the function's constant, right? So constant function, derivative is 0, okay. So the derivative is 0, but there's no local maxes or mins. So is Fermat's theorem false?
It's not like a closer deal.
Not quite. We're actually not dealing with a closed interval anymore.
It's just not a local maximum. Like,
It's not a local min either.
yeah, it's just not either. But you can still have a derivative equal to 0.
Okay.
I'm guessing part of just a small part of some bigger theorem.
Yeah, it's kind of a small part. If my discrete math students are in here, this is actually proof that the converse of this theorem is false. So the converse is reading it backwards, okay? So the reason why this is confusing is because we have this and statement and we're saying if it has a local max and the derivative exists, then this thing is true, okay? And Fermat's theorem is very confusing because of that, because a lot of people read it the other way, okay? So we can still have the derivative being 0 and something not being a local min or max, okay? So I'm going to write this out. F prime of c equals 0, so the derivative equaling 0 doesn't necessarily mean we have a local min or max. Now, if we have a local min or max, the derivative can be 0, but the opposite way doesn't work, okay? So f prime of c doesn't mean a min or max. And yeah, it's kind of like part of a bigger theorem going on here, right? Okay, so we know that reading the theorem backward doesn't work, which makes this theorem very confusing, which is why I don't like it. Going on to example 12, let's see what goes on. Fermat's theorem, remember, it says if we have a local max or min, the derivative exists, then f prime of c is 0. Well, I do have a absolute and local min here, right? This is a local min. The derivative doesn't exist, right, Sam? So f prime of 0 doesn't exist. Okay, well, I thought the derivative was supposed to be 0 every time we had a local max or min. What's going on here? So why does Fermat's theorem not work this time? And statement, right? It says up here, it says, okay, if we have a local max or min, and if the derivative exists, then this can happen, right? Now, my computer science people are probably catching on a little bit faster here, but we can have something that doesn't exist, okay? If the derivative doesn't exist, we actually can't apply Fermat's theorem because we have this if statement that kind of tells us what has to be true for us to apply it, okay? So, oh, here? There's 3 types of ways derivatives can't exist, right? There's either, actually not 3 types of ways. Sorry, I'm thinking about continuity. I think a sharp corner is where it doesn't exist, right? I also said discontinuities, so jump discontinuities don't work. And I said horizontal, or not horizontal, vertical functions, something like that. So anything that looks vertical at the point, a jump discontinuity, so, or a sharp corner. Let me write that out. So sharp corner, discontinuity, or I think it's called a vertical tangent line. All these are examples of a derivative not existing. So f prime of c does not exist. Okay, this is an example of a sharp corner. The absolute value function is an example of something where the derivative does not exist there. Really good questions here. All right, so what I want to say here is you can have a local min even if the derivative does not exist. Okay, so the main reason why I tell you not to know Fermat's theorem is because it's really confusing. It doesn't really give us too much insight into like how to find like local maxes and mins. Okay, but it does give us a hint of where to look. Okay, it gives us a hint because we know that when the derivative equals 0, there could be a min or max, right? And it also says when the derivative doesn't exist, there also could be a min or max, okay? So there's 2 places that we can look to see if we have a local min or local max. It's either where the derivative does not, or where the derivative equals 0, or where the derivative does not exist. So 2 different ways we can find these local mins or maxes. Okay, let's put this all together. I put a warning about Fermat's theorem, but I think we already kind of talked about that. So let's jump to this definition here. Okay, we have these things called critical numbers. Okay, critical numbers are the x values where we look to see if we have a local min or max. It's not where there's local mins or maxes, but it's where we can look to see if there is one or not. Okay, so critical values are where either the derivative equals 0 or where the derivative does not exist. Okay, so 2 things that we have to look for critical values. One thing I do want to harp on is that critical values are x values. Okay, I know that we said maxes and mins are y values. Critical numbers are x values. Okay, now if that was really abstract, let's do an example and it might kind of give us an idea of what we're actually looking at here. In this example, we have x cubed minus 3x squared plus 1, okay? Critical values talk about the derivative, so maybe we should find that, right? So what's the derivative of my function here?
Squared minus 6x.
3x squared minus 6x, good. Okay, my critical numbers happen where the derivative is either equal to 0 or does not exist. So maybe I should set my derivative equal to 0, right? How can I solve this equation?
Factor on x.
Yeah, both of these guys have an x. So I could take an x out, and what would be left inside?
3x minus 6.
Good, 3x minus 6 equals 0. When I have two factors equal to 0, you can always kind of separate our factors. So we can have an x equals 0 and a 3x minus 6 equals 0. Okay, well, this guy over here is already solved. Guess we can solve the right-hand side equation first by adding 6 on both sides, right? So we have 3x equals 6, and then we can divide by 3. So x equals 2. Okay, so I found out that the x values where my derivative equals 0 is x equals 0 and x equals 2. Now we're not done yet because we also have to figure out where our derivative doesn't exist. Okay, where does my derivative not exist? Yeah, sorry, I asked like a double negative there, but yeah, nowhere, right? This derivative is a polynomial, right? Polynomials exist everywhere, okay? So polynomials exist everywhere. Okay, so there's really no place where this function does not exist. So we don't really have to think about it when we have a polynomial, okay? So my critical numbers are my x value, x equals 0, and my x value, x equals 2. Okay. Any question on example number 13? Okay, now to put this into context, these are the two x values where you might think that we have a local max or min. They're not telling us that we do have a local max or min there, but it's where we would want to look. Let's flip our page over to example number 14. I want to do this one because it is a little bit harder than example 15 or than example 13. But I think it'll give us a little bit of an idea of where to go from here. Okay, we have our function x 3/5 times 4 minus x. Critical numbers mean first we should probably find what the derivative is, right? If I want to find the derivative, there's actually two ways we could do this. Any ideas? You can do product rule, okay. Yeah, there's two ways. We could do product rule or distribute, right? Yeah, I kind of agree with you on that. I think distributing the x over would make it a little bit easier to do just because the product rule is messy. You have to multiply things. Let's do this method. Okay, so f of x is if I distribute this over, 4 times x to the 3/5 is 4x to the 3/5, right? What's x times x to the 3/5?
X to the 8/5.
Yep, x to the 8/5. Remember, we add the exponents when we multiply. Okay, so we have 4x to the 3/5 minus x to the 8/5. That's my original function. Let's find its derivative. Okay, what's the derivative of 4x to the 3/5?
Over 5x to the negative 2.
Nice. I'm gonna split it up into 2 steps here, but nice job on that, Sam. It'd be 4 using the power rule, 3/5, and then x raised to the 3/5 minus 1, right? I know I'm kind of going overkill here, but I want everyone to see all the steps going on here. And the same thing goes for the second one, right? I bring my power up to the front, and the power goes down by 1. Okay, does everyone see how I got here? Good. Cleaning this up, we got 12 over 5 we've got x to the 3/5 minus 1 is -2/5. Okay, and then we have 8/5 x to the 3/5, I think. Okay, so this is my derivative. Now it looks a little funky. Let's try to make it into a fraction. Fractions kind of are very helpful when we deal with critical values, and I'll show you why in a little bit. Okay, so I guess we need to write this in terms of fractions. How can I write x to the -2/5 in terms of a fraction? What does a negative exponent do? Raise it to the bottom, right? So this is essentially 12 over 5x to the 2/5, and then minus 8/5 x to the 3/5. Are we all good here? Good. Okay. What I want to do is solving this for x is kind of hard to do if it's not one fraction. So maybe I should take this and bring it into one big fraction so it's easier to work with the numerator and with the denominator. Okay, so to do this, I need a common denominator. It looks like the denominator both has a 5, but maybe I want the denominator on both to be 5x to the 2/5. Any idea on how to make that happen? What would I need to multiply this function by?
Multiply both sides. One side by 1/2x to the 2/5.
I could do that, but that would offset my equation. It wouldn't make it the same equation. But I could multiply it by x to the 2/5 over x to the 2/5, right? And that's better because this is essentially multiplying by 1, which we can always do to anything, right? Okay. So the reason I did that is this makes this 12 over 5x to the 2/5 minus 8x to the 3/5 x to the 2/5 over 5x to the 2/5. So I just multiplied the numerator and the denominator. Okay, now the denominators are the same. It makes it really easy for us to subtract. But before I do that, what's x to the 3/5 times x to the 2/5? So what do I get when I multiply these guys together?
8x.
Not 8x.
X to
I
the
heard-
6 over 5.
What do we do when we multiply two things with the same basis? What do we do with the exponents? We add them together, right? So this turns into, let me write this out here. Let me write in a different color too. This is x to the 3/5 plus 2/5. Okay, and as John said, this is x to the first power. I know, it works out pretty nice, doesn't it? Oh, I didn't realize you put the 8 in front. Okay, sorry, Jude. You got it right. I'm so sorry about that. All right. Okay, so this becomes 12 over 5x to the 2/5 minus 8x over 5x to the 2/5. Okay. Once we're here, looks like the denominators are the same. So we can actually make this one big fraction, 12 minus 8x over 5x to the 2/5. Okay. And this is finally my derivative. Okay, so that is f prime of x. Okay, I did all this algebra. And the reason I did this is because I wanted to consolidate everything into one fraction where I can kind of pick apart the numerator and the denominator and work with those by themselves. Okay. Well, we're not done yet. We have to find the critical numbers of this derivative or of this function. So the first thing we need to look for is when this derivative equals 0. Okay, so maybe what I should do is set my derivative equal to 0. Right, that's about a good step we can do. Okay, my derivative is 12 minus 8x over 5x to the 2/5, and I'm going to set that all equal to 0. What can I do on both sides to make this a little easier? Dividing, I mean, you could, but it wouldn't help too much.
Multiply.
Yeah, multiplying by the denominator usually works because yeah, and sometimes the wording is weird. 5x to the 2/5, 5x to the 2/5. Okay, so on the left-hand side, we're left with 12 minus 8x, and on the right, we have 0. Now, whenever we set a fraction equal to 0, what are we essentially doing? Did I have to start with my fraction, or could I have made it a little bit easier? So 12 minus 8x, this is the numerator of my derivative, right? So if you want to just cheat and not write down a few steps, when you set your derivative equal to 0 and it's a fraction, you can essentially just start with the numerator equal to 0. Now, if you feel more comfortable doing this step, that's fine. But when we set a fraction equal to 0, it's really just solving the numerator equal to 0. Okay, we're not really doing anything with the denominator. Okay, does that make sense? Okay. All right, solving this is pretty easy. We can subtract 12 on both sides and get negative 8x equals negative 12. We can also divide by 8 or negative 8, right? And we get x equals 12 over 8, which I think is 3 over 2. Okay, so I found where my derivative equals 0, 3 over 2. Is that my only critical number? What else do I have to look for? Where it doesn't exist, right? Critical numbers are where the derivative equals 0 and where the derivative doesn't exist. So we have to find the x values where f prime doesn't exist. How can I do that? Yeah, we have a denominator going on. Remember, you can't divide by 0, okay? So setting the denominator equal to 0 is going to find all the x values where the denominator is equal to 0 or where the derivative doesn't exist, okay? So the way we go about this is I'm going to set 5x to the 2/5 equal to 0, okay? And let's see if we can solve this. I guess I have to divide by 5 on both sides. So we have x to the 2/5 equal to 0. What do I have to do to get x by itself? What should I do on both sides?
The power of 5.
Yeah, right. We have a denominator of 5. So because of this, maybe we should raise something to a power of 5. I'll do that in a different color. Okay. What am I left with on the left when I do this? X squared. Good. It cancels out the 5. On the right, 0 to the 5th power is still 0. What do I have to do now? Square root. Remember, plus or minus sign when you take the square root, but it doesn't really matter because it gives us x equals 0. Okay, so this is how we solve an equation with a fractional exponent. Okay, so we also have x equals 0 as a critical number. Any questions on this example?
This example worked out luckily. We had a fifth root in the denominator, but what can I say? You know how it doesn't exist if or negatives can't exist if it's in a square root or any even root.
Oh, okay. Yeah, I think that is true. I think with critical number problems, it wouldn't really be helpful if we found like that a square root. I don't know if I'd ask you that. I feel like it wouldn't be very useful because critical numbers are used to figure out where the local mins or maxes are. And if there's like a big gap of things that are critical numbers, then it would kind of be weird to check every single number in that gap, right? So I don't know if that would be too useful, but that is a good question.
Because it probably stop existing in the, what's the opposite of a derivative?
An integral.
It would probably stop existing in interval too, right?
Yeah, I think with the square root type functions, I think we're looking for critical numbers on their domains. So if there's a big gap of things where the function doesn't even exist, then I guess we wouldn't consider them critical numbers at all, because it's what we look at for to find the local mins or maxes. So I think if there's a square root, we would only look for the critical numbers where it actually exists. And we would only look for specific numbers where the derivative doesn't exist, instead of like intervals. That is a good question though. Yeah.
So I'm kind of still confused of why we're searching through the denominator for critical point when that it doesn't count in the original as an x.
Well, it doesn't. Okay, let me show you an example of where something where the derivative doesn't exist would become a local min. Something like this, right? Now, there are ways where the derivative doesn't exist and it's not an absolute value. And I think that's where we have, this is kind of tricky. Maybe let's try this. There are some functions that look like this and have a hole in it. And we might have a number here, actually a number here, okay? Here, I guess the derivative wouldn't exist because the function doesn't exist, but it's still a local max because the function's defined elsewhere. Does that make sense? So I guess that's what we would also be looking for. So technically, yeah, I think critical numbers still would be important even if we have a denominator. I don't know if that helps. So I'll come tomorrow. I can give you an actual example, but there's functions that have holes in them where the derivative doesn't exist, but then they're defined elsewhere. And I think that might be why we would be looking for a local min or local max. Yeah.
So what are we using these values for? Like the x value of the
Yeah, so the critical numbers give you an idea of where the local mins and local maxes are. Okay, and we're going to use that when we talk about a different theorem that tells us exactly where the absolute mins and absolute maxes are without having to draw the function first. And I think that's where the critical values come up mostly. They also come up in optimization questions, which are essentially doing the same thing. But yeah, I think we would still have to find critical. I think when we do more examples with these, we'll also see that sometimes where the derivative doesn't exist, we still have a local min or max. But I think we might have to wait for that in the future. Yeah, sorry to not answer your question right away, but I think that's why we're gonna do that. Okay. All right. Any other questions? I like all the questions. It's good. All right. Then I think what we're going to do is we do have a quiz review to go over. I'm going to do some thinking today and try to come up with more stuff. But let me pass out this quiz review. Okay. Just like last time or a couple weeks ago, I will post the answers to the quiz review later today. So if you have somewhere to be